Hello friends, dear learners and my dear student. First of all, I take an opportunity to welcome you at my TY BSc Analytical Chemistry class. Student, I am Dr. S.R. LABHADE, working as Associate Professor in Chemistry at CH-344 in Nasik. Student, in today's lecture we discuss the principle of chromatographic separation by using matchbox model. Friends, we know that chromatography is a name given to those analytical separation method in which components of the sample are separated, identified and estimated via their separation using suitable solid or liquid as a stationary phase and liquid and gas as a mobile phase. In addition to this, we also know that every technique of chromatography consisting of stationary phase and a mobile phase. Solid or liquid as a stationary phase or liquid or gas as a mobile phase. Sample containing different components when placed in between these two phases. Mobile phase dissolves the sample component and carries them through the stationary phase. When this sample component comes in contact with the stationary phase forms specific bond with the sample component and retards or holds those sample component. Therefore, mobile phase provides a driving force to the sample component while stationary phase provides a retarding force. Relative magnitude of driving force and retarding force, sample components migrates with a different speed through the stationary phase and get separated. Therefore, in chromatography, samples are separated on the basis of differential migration process. Student, we know that on the basis of type of stationary phase used, chromatographic methods are broadly classified into two categories. Number one is called as adsorption chromatography and number two is called as partition chromatography. In adsorption chromatography, solid adsorbent material is used as a stationary phase and relative adsorption towards the stationary phase, sample components are get separated in adsorption chromatography. In partition chromatography, stationary phase is liquid. On the basis of solubility of the sample component towards the stationary phase liquid, sample components are get separated. Therefore, solubility difference is a basis on which the sample components are separated in partition chromatography and differential adsorption process is a phenomenon on which the sample components are get separated in adsorption chromatography. Student, in today's lecture we discuss the principle of chromatographic separation by using a partition chromatography. In a partition chromatography, we know that stationary phase is liquid and this stationary phase liquid is made steady or stable by their coating on the adsorbent material. Therefore, this is the adsorbent material initially packed into the column and over this a liquid is coated and this liquid acts as a stationary phase. Therefore, mobile phase is also another liquid. Therefore, both stationary phase as well as mobile phase are liquids in this type of chromatography and this is a partition chromatography. Here, condition is that the stationary phase liquid which is coated on this adsorbent material and mobile phase liquid which is percolated through this adsorbent material, these two liquids must be immiscible with one another. Therefore, in partition chromatography, if stationary phase is liquid and mobile phase is liquid, then these two liquids must be immiscible with one another. Otherwise, here there is no stationary phase and no mobile phase if both liquids are miscible. Therefore, here in liquid-liquid partition chromatography, two liquids must be immiscible with one another, that is not soluble with one another. Now, based on this, we can discuss here the principle of liquid-liquid partition chromatography by using a matchbox model. In a matchbox model, here there are two columns. One column that is a column of stationary phase and another that is this is a column first that contains solvent first. This is column second. This is column second containing solvent second, and this is a mobile phase. Therefore here stationary phase that will be present in one side of this matchbox model and mobile phase is present to the other side of this matchbox model. Such imaginary two liquids are considered in matchbox model. Here these two liquids are impossible to show in a single column. But here this is the stationary phase present in the column and this is mobile phase passing through the column. But here stationary phase and mobile phase liquid are in contact with each other, and that we are showing by using two columns of this matchbox model. Here in matchbox model there are number of such boxes, and these boxes containing a stationary phase liquid and these boxes consisting of a mobile phase liquid. Therefore this is box number 1 of the mobile phase. 2, 3, 4, 5, 6, so on. This is box number 1, 2, 3, 4 and so on of the stationary phase. Now we discuss how this matchbox model actually work. Suppose for example, if we have two components, that is A and B. Suppose we have 1 mole of A and 1 mole of B, and these two components we have to separate by using this matchbox model. Therefore, initially these two components are placed into the first column. That means at the top of this column, this A and B is placed. That means that is here in the first column of the column 2 of the matchbox model. That means this is a mobile phase, and we know that sample components are carried by the mobile phase. Therefore, when we place this sample at the top of the column, that will be in the first box of the mobile phase. Then this liquid we are continuously adding into the column. That liquid takes the sample, percolates through the stationary phase. Suppose for example, when these two liquid, when this box we put to downward direction, next position will be like this. That is 1A and 1B. Now here 1A and 1B that is present in the mobile phase. Here stationary phase box is empty that does not contain a solid molecule, but it contains a solvent molecule. Now here on the basis of relative distribution of the solid A and B in two solvent, separation takes place. Suppose for example, if here A and B, if A and B both are insoluble in solvent first, then there is no separation. That means if A as well as B, if it is insoluble, A and B is insoluble in this stationary phase, then A or B does not transfer into the stationary phase, then separation is not possible. Second condition is that if A and B both are equally soluble in both solvent, means stationary phase solvent, mobile phase solvent, at that time whatever A is dissolved into this stationary phase, same amount of B is also dissolved into this stationary phase. That means here again separation is not possible. That means if both components are insoluble in stationary phase, then separation is not possible, and if both components are equally soluble in stationary phase liquid, that means in mobile phase liquid also, that means there is no separation of the sample component. Third condition is that if A is 100% soluble, 100% soluble in solvent first, that means in stationary phase, and B is 100% soluble in solvent second. Then here a single distribution that gets separated these two components. That means single box is required only for separation. If A is 100% soluble means total A is get transferred into this box. And if B is 100% insoluble in this solvent but 100% soluble in mobile phase, that means B is not transferred into this stationary phase. Therefore here if solubility difference is more, that is 100% soluble in this solvent, that means 100% insoluble in this solvent. That means if A is 100% soluble in stationary phase, total amount of A is get transferred and B remains in mobile phase. That means single box or single equilibrium is sufficient to separate these two components A and B from one another. Third condition, practically such a type of solubility difference does not possible in case of a component A or B or any component. Therefore practically A is not 100% soluble into this solvent and B is not 100% soluble in mobile phase. Therefore we assume condition that A is 50% soluble in both solvents. In both solvents, that means stationary phase as well as mobile phase, and B is 25% soluble in stationary phase and 75% soluble in mobile phase. That means in solvent second. Therefore here A is equally soluble but B have a solubility difference. B is only 25% soluble in this solvent and 75% soluble in this solvent. Therefore, based on this, we discuss how this separation taking place in batch box model. Now we discuss the different steps involved in the separation process by using a match box model. We know that we assume here A is equally soluble in both solvents, stationary phase solvent and the mobile phase solvent, while B is only 25% soluble in stationary phase and 75% soluble in mobile phase. This is the stationary phase liquid, this is mobile phase liquid, both are liquids. Here, if A is equally soluble in both solvent means half of the A will be given in stationary phase and half of the A will be remains in mobile phase. That means it get distributed in this fashion, one half A and here one half A. That is A is equally soluble. While what is about B? B is 25% soluble in stationary phase and 75% soluble in mobile phase. Therefore, B get distributed as 1 by 4B, that is 25%, and here A 3 by 4B. That means here on the basis of solubility difference, this A and B get distributed between the two solvents. If solubility is 50%, that means A is equally distributed into both solvents. Here B is 25% soluble means 1 by 4B is given in the stationary phase and 3 by 4B will be remains in mobile phase. Now if we put a extra mobile phase and if we push all these boxes to downward direction, the next position will be like this: 1 half A and 1 by 4B. Here a pure mobile phase, again here 1 half A and 3 by 4B. This will be the next position when we put a fresh mobile phase box and we will push all these boxes to downward direction. Therefore here box number 1 of the stationary phase is in front of box number 2, that means it consisting of pure mobile phase, and here mobile phase containing some amount of A and B, that is Now again, depending upon the solubility, these A and B are get distributed into two solvents in this way. As A is equally soluble means again half of the A is given in stationary phase and half of the A will be remains in mobile phase. That means 1 by 4 A remains in stationary phase while 1 by 4 A given in a mobile phase. Now how B is distributed? Initially 1 by 4 B is present in stationary phase. We have to distribute it as a 25% and a 75%. Therefore 1 by 4 into 4 divided by 4 means 4 by 16 means 1 by 16 plus 3 by 16. Therefore here 1 by 16 B will be remains in stationary phase liquid while 3 by 16 B will be given in a mobile phase. That means here again there is distribution of this A and B on the basis of solubility and that will be taking place in this fashion. Similarly, there is distribution of this A and B with these two solvents. Again A is equally soluble means 1 by 4 A will be remains in mobile phase while 1 by 4 A will be given in a mobile phase. 1 by 4 A will be remains in stationary phase and 1 by 4 A is given in a mobile phase. Therefore here again we have to distribute B as a 25% and 75%. For this purpose again 3 by 4 B into 4 divided by 4 means 12 divided by 16 which is equal to 3 divided by 16 plus 12 divided by 16. Therefore here again 25% means 3 divided by 16 B will be given here and 12 divided by 16 B will be given here. That means here if we have to distribute that B as a 25% and 75%, you can multiply that factor with 4 and divide that factor with 4. And therefore here that will becomes 12 by 16 means 9 by 16. Therefore 9 by 16 will be given in stationary phase. In this way here B is get distributed as 3 by 16 means 25%, 9 by 16 as a 75%, and this distribution will be taking place in this fashion. Now here when we place another fresh box and if you put all these boxes downward direction, here 1 upon A, 1 upon 4A, 1 upon 16B, here 1 by 4A, again 3 by 16B. Similarly now this box is here 1 by 4A, 9 by 16B. This box is here that is 1 by 4A and 3 by 16B. Here is pure mobile phase and here is pure stationary phase when we push all these boxes to downward direction. Now again here this is a distribution of A and B with a two solvent. Here there is fresh stationary phase. Again there is distribution of A and B with this fresh solvent. That will be distribution similar to we discussed as earlier. That means again 1/2 A, this is here 1/2 A, that means 1 by 8 A is given here, 1 by 8 A will be given here. That means here 50% get distributed. Again here 3 by 16 means 1 by 16 into 4 divided by 4, that means 4 by 64 means 1 by 64 and 3 by 64. Therefore here 1 by 64 B is here and 3 by 64 B will be here. That is here this box in front of this will get distributed in this fashion. Now here, 1/2 A and 1/2 A present in both the boxes. That means A is equally soluble. Therefore, there is no distribution of A when here mobile phase also contain 1/4 A and stationary phase also contain 1/4 A. But here we have 3/16 B in stationary phase plus 3/16 B in mobile phase. That means 6/16 B is total. 3/16 plus 3/16 means 6/16. Then you have to distribute it as a 25% and that is 12/32. That means here 3/32 plus 9/32. That means 12 into 6 into 2 means 12 divided by 32. 12 means 3 plus 9 and therefore 12/32 can be distributed as 25% as a 3/32 and 75% as a 9/32. Therefore here a 3/32 B will be remains in a stationary phase while a 9/32 B will be given in mobile phase. Again here we have 1/4 A here which is here like this and 9/16 B. Again here A will be distributed as a half. That means 1/8 A will be given here and 1/8 A will be given here. That means here A is distributed equally. Now 9/16 we have to distribute as a 25% and again 9/16 into 4 divided by 4 means 36 divided by 64 means a 9 divided by 64 plus 27 divided by 64. Therefore 9/64 will be remains in stationary phase while 27/64 will be given in a mobile phase. In this way here this distribution will be taking place 1/2 A and 1/2 A. That means 1/8 A, 1/8 A equally soluble. Again here 25% soluble, 75% soluble. Here is a fresh solvent, therefore this is called as distribution. But here two boxes containing two components and therefore there is again redistribution of these two components on the basis of their solubility. And that distribution will be like this. Now if we discuss next step here 1/8 A, again 1/64 B, then 1/4 A and 3/32 B, again 1/8 A, then 9/64 B. This will be here. Now this box is here. 1/8 A, 27/64 B. Similarly here this is box 1/4 A and 9/32 B. Again here 1/8 A and 3/64 B. Here is pure mobile phase and here is pure stationary phase. Again depending upon the solubility difference, A and B are get distributed into the two solvent. And finally here if we write this here we have after this we have 0.03A and 0.001B. Here 0.03A and here 0.003B. That is 25%, 75%. Therefore here again 0.12A, again 0.12A, here 0.02B, here 0.06B, again here 0.18A, 0.18A, here 0.05B, 0.15B, and here next box is 0.12A, 0.12A, 0.11A, 0.33A, similarly here 0.03A, again 0.03A here, 0.08A, and B, this is B, this is B, and here this is also a B, therefore 0.24B. Therefore, in this case, if we carry out 5 equilibria, the distribution is like this. In this case, you will observe that here A and B both are migrating through the mobile phase as well as stationary phase. But concentration of B is more in mobile phase compared to concentration of B in stationary phase, because B is more soluble in mobile phase. Therefore, if we carry out number of such equilibrium, then finally we have B gets separated from A. That means in next box we have only B, there is no A. And in stationary phase we does not have a B, because concentration of B decreases here 0.001. That will be decreases if we carry out number of such equilibrium or number of such a distribution equilibria. Therefore, in this case, we can discuss here the matchbox model, how does it useful for separation of two components having little solubility difference. If two components have more solubility difference, then less number of equilibria are required. And if two components have less solubility difference, then more number of equilibria are required to separate the two components. That means here separation efficiency not only depends upon the number of equilibria that will be taking place in the matchbox model, but also the solubility difference. If component A is 100% soluble in stationary phase and B is 100% soluble in mobile phase, then a single box is sufficient to separate them. But here, practically it is not possible, and therefore on the basis of solubility difference, this matchbox model work. And if more is the solubility difference, less number of equilibria are required to separate those components from one another. Now here, in this case, in this matchbox model, this single box represent a single distribution equilibrium, and this single distribution equilibrium is called as a theoretical plate. And that theoretical plate is important in chromatographic separation, and on the basis of that theoretical plate, the chromatographic separation takes place. Here these boxes are represent the theoretical plate. If particular column have more number of such theoretical plates, that means more number of equilibria are possible in that column, then separation efficiency of that chromatographic column is more. Now in next lecture we discuss what are the theoretical plate and what is their role in a separation process. With this we stop here. On the basis of this you can discuss, you can write an answer of question, following question, that is explain the principle of liquid chromatography by using a matchbox model. Student, with this we stop here. Thanks for joining me. Keep learning. Happy learning.